Hello and welcome back. So, in this video we will look at MAP or maximum posterior estimation Bayesian regression. The material is inspired by a PRML book by Christopher Bishop and many images are also taken from the book. Okay. So, we will just consider it in the context of linear regression. Okay. So, we have this model typically this is how we model in the case of linear regression, where phi of x corresponds to some polynomial functions of x or any other functions of x. So, typically 1 x, x square, x cube, so on. Okay. We are given training data points pairs xi comma yi with I ranging from 1 to m. We saw earlier that if the points xi yi are independent and identically distributed, then the probability of observing the data set is nothing but the probability of the product of the probabilities of the individual data points. Okay. So, this is the likelihood function, likelihood of data, okay, given the model. Okay. So, that is how we had earlier modeled it, and when we took the log likelihood, negative log likelihood, we ended up with the mean square loss function if we model this as, if we model each one of these as a Gaussian function. Okay. Now, if we use Bayes rule, so basically we want to calculate P probability of W given y and x, okay, given the data. So, y comma x is the data pair, training data pair. Then using Bayes rule we can write it in this form. So, where this is our likelihood and this is the prior. Okay. The denominator you can call it as observing the probability of data, which is a constant, right. So, if we expand out the likelihood terms, we again once again end up with the products of individual probabilities with a normalization factor here, which is again evaluates to a constant because it depends on the training data set alone and not on W. Okay. So, it has no impact, it has a scaling impact. So, we can always absorb it as a constant. Okay. So, now we take the we think about what do we do the prior. So, if you go back again, I said this was a prior, I did not exactly mention what it was. It came out of the application to the Bayes rule to the posterior probability. Just to mention again, this is the posterior probability. So, the prior seem to just come out of the application of Bayes rule. So, we have to see what it means. Okay. So, if we recall the polynomial pair fitting example we had, as the degree of the polynomial increased, there was overfitting, which again led to very large values of W. Okay. Remember, very large values of W. Now, it was desirable at that time that the values be low, right, because the W was becoming very large to compensate for individual data points. So, it was overfitting. So, how can we enforce that? We can enforce that by saying that the prior should be a Gaussian, okay, with 0 mean and a standard deviation, which we can either estimate or we can either set as a hyperparameter by cross validation. Okay. And in this case we can assume that the covariance matrix of the Gaussian is a diagonal matrix. So, how does it help avoiding large values of W? So, if we impose the prior that W is drawn from a Gaussian distribution, then we are looking at the function something like e raised to, remember, 0 mean. So, some normalizing factor here. Okay. So, now, and I am also not writing out the let us say there is some alpha squared, the variance parameter alpha squared I am not writing that out, but you can just look at e raised to minus W squared. So, if you plot the PDF for W on this axis, again W can be positive and negative, you will see that it can be something like this, right. This is what you have seen. So, for very large values of W, so this is the PDF. So, if we for very large values of W, the probability of getting that W drops off exponentially, and we can actually control this width as a hyperparameter. So, then we can actually make it very sharp also, so that we can only get very small values of W. So, by imposing the prior, we make sure that there is no overfitting. That is the advantage of using a prior. So, to recap, we want to estimate the what we call the posterior distribution, like we want to directly estimate W. This is what we do when you do the optimizing gradient descent, right, you actually estimate W. So, from a probabilistic point of view, we want to estimate W given the data set y comma x. Now, if you use Bayes rule and rewrite it in this form, it turns out to be a product of likelihood and prior. Now, we saw that by taking the log likelihood, we end up if the likelihood function is modeled as a Gaussian, the log likelihood leads to the least squares loss function. So, and that is what causes overfitting in many of our problems. By looking at the posterior, we have this term prior, which is multiplicative, and what we do is we can impose any kind of prior on it. So, it has to be a probability distribution. One of the most commonly used prior is the Gaussian distribution, and if you plot the Gaussian distribution, you will see that for very large values of W, the probability of getting the W kind of goes to 0. Okay. So, now we just explicitly model this P of W is n is the normal or Gaussian distribution with some alpha square, a diagonal matrix as the covariance matrix. Again, it can be a learned parameter or a hyperparameter. Then if we write out the posterior distribution of W given y given the training data, so it can be written in this form. Once again, I have pointed out that the denominator is again a constant, and again recall that you can also model the likelihood here as a again as another Gaussian, where the mean is given, estimate of the mean is given by the model W transpose x. Here I should, to be more general, I should try to transpose phi of x. Okay, you can put that in there. Again, we assume a, in this case too, some sigma squared I parameter. Okay, some sigma squared where all the variances are the same. Okay. So, if we take again, if we take the negative log of your posterior probability, then you will see that it usually simplifies to this, because it is a log of 2 exponents. So, then the exponent comes down, then we see that it comes to this loss function, which is your least squares loss function plus an L2 regularization term. So, recall that when we did the polynomial curve fitting, by adding a L2 regularizer, we were able to prevent the weights from blowing up and also to prevent overfitting. Okay. So, that is what which is the same as evaluating the posterior probability or the maximum or the map. Okay. So, you can actually solve this problem by using gradient descent, and you get a value of W, which we call the map estimate. Okay. That is one way of solving using gradient descent. However, we can actually, if you look at this log probability, the log probability can be rewritten in this form. So, what is this? If you recall, we have seen expressions of the type x minus mu transpose sigma inverse x minus mu. If you recall, this is the exponent in a Gaussian, exponent in the Gaussian. So, it turns out that if we use the Gaussian model for the likelihood and a Gaussian prior, it turns out that the posterior also is as a Gaussian, and we can actually bit square, there is a trick called completing the squares, then you can get it into this form, from which you can directly estimate W tilde. This is again the same as W map and the corresponding covariance matrix. Okay. Okay. So, if you see that W tilde depends on the covariance estimate, which contains contribution from both the data and also our constraint that we impose in the form of a prior, the alpha squared, and it goes into determining the W tilde or the W map estimate. So, this is the same as the W map, W tilde is the same as the W map estimate, that is a mean estimate that we have. Okay. But once again recall, see that it is still a point estimate of W. So, you will get one value of W, and you use that W to actually calculate for every new test data, you will do phi x test data to get a point estimate of your output y tilde, that is typically what you get, right, that is what you do all the time. Now, that is nice, but then we will go one step further and do what is called Bayesian regression, where we do a predictive distribution on y tilde. So, what we want is an error bar on your estimate y hat. Y hat is what you predict, but it is just one number that is thrown out by, even if you use map or whether you use MLE, just one number that comes out. What would be interesting in many cases, useful in many cases, is to have an error bar on your estimate, and that is where Bayesian regression, fully Bayesian regression comes in. But we will look at this map estimate with a slight example. Okay. So, let us consider this problem where your model is W naught plus W1 x. Okay. So, you are given training data points xi comma yi. Okay. So, in this toy example, a W naught and a W1 were fixed for various value of x, you get generated yi's, xi's, we generated yi's, and then some noise was added to the yi's. Okay. So, that is the data point. So, then okay, we start off with our prior, right. So, the every row, the leftmost column is the likelihood, the middle column is the prior, which also doubles up, it doubles up at the posterior also, and the right one is your predictions, if you can think of it that way, that is the data space. Okay. So, first step we have the prior, where we, as we saw, we have a Gaussian prior, right, we have a Gaussian prior. That is what, if you plot this out, that is what this will look like, where W equal to 0, that is where it is, will correspond to the maximum value and it will drop off exponentially as you go away from 0, okay, on both the axes. So, the axis, this axis is W naught, that axis is W1. So, we are plotting this E exponential distribution as a function of W naught and W1. So, that is our prior distribution. From that prior you draw 2 samples, sorry 6 samples, and you see the red lines here, the red lines here corresponds to the 6 samples of W naught. So, you will draw 6 pairs of W naught W1, okay, 1 through 6, and for each one of them you can calculate W naught plus W1 x. For your training data, now you have training data x, you can do that, or from any or arbitrary values of x you can calculate. So, if you do that, then for every x there is a y, right, x comma y. So, using that you can actually plot a line, right. So, this is the equation of the line. So, y is W naught plus W1 x. So, if you draw 6 pairs of W naught W1 from here, you can get 6 lines in the xy plane. So, this is x and this is y, okay, that is the data space, right, that is nice. So, we actually have the training data, right, let us say we observe one data at a time. So, in this case we have just try to highlight it in something that is visible. So, if you look, this is the data, this is in white cross, I do not think it is very clear, but that is where that is an observed data point. Okay. So, you have one data point, okay, that you got, and if you have the data point, then let us say you have one x, right, one xy, you have one xy pair has been observed. Okay. So, then what can you do? You can calculate the likelihood. How do you calculate likelihood? You remember it is some exponent, I am ignoring all the constant, y minus W transpose x squared by some sigma squared, okay, something like this. So, you can actually calculate the given x and y for various values of W naught and W1, you can calculate this likelihood. So, and the dark red bands corresponds to regions of maximum likelihood for this one data point that we have observed. So, now you take this likelihood and multiply it with the prior. Okay. So, likelihood times prior gives you the posterior distribution, which is this one. Okay. So, now you can draw 6 more points from this posterior distribution corresponding to W naught and W1, 6 pairs, and you plot 6 different lines here in the xy plane. So, then you go back here, you observe one more data point, you can recalculate again, you can calculate the likelihood for that data point, again it gives you slightly different likelihood distribution. So, now this is the new prior. So, this is your new prior, this prior times your likelihood will give you your new posterior distribution, from which once again you can draw 6 pairs of W naught and W1 and plot this line right here. Okay. So, you can keep doing that. After the 20th data point, you will see that the posterior distribution has become very sharply peaked, right. There is one everywhere it is 0, but it has very maximum value at some point, and if you sample once again 6 data points from this distribution, you will get these lines here, these red lines here, which are actually fitting all these data points, if you think about it. Okay. So, by sequentially considering data points x comma y and each time evaluating a posterior distribution, but then using that as a prior for the next time that you observe a new data point, you can actually come to the converge to the appropriate posterior distribution. So, this is how you do map estimate, if you think about it probabilistically. Another way of looking at it, if you think about it, you see that by sampling from W, right. Now that you have this distribution, you can keep sampling from W and you can keep estimating for every x comma y, for every x, in case we want to estimate y, for every x you can sample from W many times and you can estimate a y. Okay. So, that kind of gives you an error bar on your estimate, okay. But those error bars will tend to be very similar across the board because W is completely determined by your training data. So, the new x that you are using for which you are predicting y, there is no impact on the error bar, okay. So, you will get a similar error bar for pretty much depending on the training data set, that will determine your error bar size, okay. So, this is again, if you think about it, is just a point estimate. So, how do you get a point estimate? Now that you have a very sharply peaked distribution for W naught and W1, you can look at argmax. So, what is the W naught and W1 which corresponds to the maximum probability, okay. You search that space and you will be able to determine the pair W naught and W1, that is still a point estimate, okay. What we want to do next is, since we still only have point estimates, what we want, like we said, is we want the predictive distribution, okay. Predictive distribution means we want a distribution on our prediction. So, that is probability of y test given x test, right, crudely speaking, and your training data, I am going to call this D and the parameters W, okay. That is what we want. We want an error bar on our prediction. If you think of it very in a very simple sense, we want an error bar on our prediction directly, okay. What is the error bar on the prediction? So, the idea behind Bayesian regression is to determine the predictive distribution itself, okay. So, how do we go about doing that, okay. So, if you pay attention to this, what we actually want, we want this distribution. So, we want for a new x test, what will be the probability of y test, the output for new data point given the new data point and the training data, that is what we want, okay. So, that we can write using the sum and product rule of probabilities. So, this is sum rule. So, P of x is summation over y, P of x comma y. So, we introduce this variable, random variable W, which is the estimate based on our model, and then we marginalize over it. So, the summation is just replaced by the integral, okay. The second rule is the product rule, where P of x comma y is P of y given x times P of x. So, in this case P of y test comma W, we use this expression to decompose into two products. P of y test comma W is P of y test given, because we retain this conditional aspect, times P of W, okay, given x comma y, okay. So, this is the a short derivation for how to get to the predicted distribution. Now, why do we want it in this form? So, we will go one step further. We have written P of y test given x test x y W as P of y test given x test and W. So, we have left out this training data. The reason is because it does not really matter, because W captures all the information in the training data, okay. W captures all that. So, we can still estimate W from the training data, it is not a problem, and so we can just leave out, so we can leave out the dependency on x comma y because it is already been taken care of. So, and we have this, okay, and this we know is the posterior distribution. This we know what this, we have modeled this. So, we can model this as a Gaussian, this also we can model as a Gaussian based on your, this is your kind of like your likelihood function, okay. So, this is another Gaussian, okay. So, once we have this estimate, then what, so what does this do? What is this P y test, what is happening here? So, you can think of it as, let us say we have a quantity f of x and we want to estimate the mean of that quantity, this is what we would do, right, we integrate with respect to the probability distribution. So, what we are trying to, you can think of it as we are estimating a mean of this quantity. What is the probability of y test given this input x test and our model W, okay, that we are calculating an average based on the probability distribution of W conditioned on your training data. So, that is exactly what we are looking at, okay. So, your f of x here is the P of y test given x test and W, and your P of x is nothing but the posterior distribution. So, you can think of it as a way of calculating an average over all possible realizations of W given your training data. Okay. So, what can we do with it? So, we can actually do argmax of this and figure out the Y test for which probability is maximum, that is your estimate of Y. We can also calculate variance, right, because remember we can calculate moments, right, we can calculate mean, then we can calculate f of x squared, remember P of x dx, right, and if you are 0 centered, this is the variance. So, we can calculate mean. So, for every new test data point, we can not only calculate using the argmax the mean, you can also calculate the variance. This is possible, of course, assuming that both of these are Gaussian. It turns out that this integral that you see here is generally intractable, because you cannot solve it for everything, but if you assume that these are Gaussian, then this can be actually been done, and it turns out to be another Gaussian. Okay, we won't look at exactly what the forms are, because it is a little bit confusing, but get the general idea. The idea is if we estimate this distribution, we can get, using argmax we can get the mean, assuming that it is Gaussian, and we can also calculate the variance. So, for every new test data point. Okay. So, then if you look at the output of a Bayesian regression, then so the green is the true curve, which we have noise added and we have sampled these blue circles, we have seen this before. The red is the mean estimate, right, that is the mean estimate for Y, and the spread for every data point is available. That is the variance of the estimate of the mean for every one of your test data points, and that is the prediction has this error, this band which is given here, that is the error at every point on your prediction. You see that band neatly encapsulates pretty much the green curve. So, that is the advantage behind doing Bayesian regression. So, what is the biggest problem in doing Bayesian regression is, except for some forms of P of Y give test given x W, this form is very similar to the likelihood function, which we can model this as a Gaussian, except for this forms where these are Gaussian or some very specific distribution, this integral is very hard to do. Okay. So, then these are done with what are called Monte Carlo techniques. So, numerically intensive, but the advantage is once you estimate this distribution, you can do argmax or you can do the mean of the estimate, right, you can do a mean of your estimate, you can also calculate the variance of your estimate. So, also note that you see that unlike in the MAP or the ML estimate, your output, the probability of Y test depends on your current data point also, right. So, that is the interesting thing, right. So, it takes into it is influenced by the data point. So, if you actually write this out for Gaussian models, both the posterior as well as this distribution being Gaussian, you can actually see that influence directly. It is in the textbook, so I will give you the reference to that in the forums. Okay, you can look that up. So, this ends our brief look at Bayesian regression. The idea is to get, for as far as Bayesian regression is concerned, the idea is to get a predictive distribution for your output. So, you are doing Y hat, we want an error bar on that Y hat, that is what we want. The MAP estimate is basically trying to maximize the posterior distribution, okay, and the advantage of doing that is that you can accomplish regularization. Okay. So, by imposing a Gaussian prior, you got L2 regularization. You can impose some for instance a exponential prior and you can get L1 regularization, wherein most of the coefficients will go to 0, where the probability of getting coefficients is very small. So, that way that is possible. Okay. So, these techniques are applied widely in different scenarios. This is just in the context of linear regression we have seen it. The treatment in Bishop is rather dense, but it is actually one of the best treatments available. So, I urge you to go through it. I will also provide you with the references for the textbook. Bishop's textbook, by the way, is available online for free, so you can look through that. Okay. Thank you.